Hello, welcome back to the video lecture series for Introduction to the Art of Programming Using Scala. We're continuing our look at multithreading, and in particular for this video, we're going to look at critical blocks and synchronized. So in the last video, we played with our code. We made it so we have 10 different threads, and each of these threads has code in it to add 100 million onto a given count. So, we're modeling a problem here where we wanted to add up a whole bunch of numbers, and we found that there were some problems here. So one of the problems was that we had to be able to wait for all of the threads to finish before we actually know that we have the right count. And we were able to achieve that by joining with each of the threads. But even after we had waited for them to all finish, it turns out we still didn't have the right answer. And if we were to run this, we can see that whereas I'm supposed to have a billion, I'm getting just a little over 100 million on that run. Let's see what happens if we do it again. Yep. Yeah, we're losing lots and lots of counts. And we said that the reason why this happens is because we have a race condition. Now, I'm going to take off some zeros here. So now I'm counting to 100,000 in each one, and my total count should get to 1 million. Okay. And you'll see why I decided to do that in just a second. How can we fix this? How can we get a count that is actually correct? Okay. The answer to that is, well, actually there are several answers to that. One of the answers to that is that we can make it so that two threads can't do this at the same time. Okay, so the problem that we have, as you might recall, is this race condition is being caused because this right here can be interrupted, and you can have multiple threads doing it at once, and there's only one counter here. And so if two threads load in the counter at roughly the same time, or if one thread loads in the counter before another one has finished writing to it, one of those results is going to wind up being lost. And it turns out that, as you can see from our answers, most of the counts wind up being lost in this. We lose a great deal of what we're trying to calculate here. So how can we fix that? Well, if you have a piece of code that should not be interrupted, we refer to it as a critical block. So for this particular program, the critical block is right here. If you had like a bank account, the methods for withdrawing and depositing would be critical blocks of code. You should not have two threads withdrawing or depositing or doing both simultaneously from a single bank account. You need to have them so that only one can happen at a time. So how do we do this? Well, there is a method called synchronized that exists on pretty much every object in Scala. It's part of any ref. You might remember the inheritance hierarchy for Scala objects. And so every time that you create a class or an object, you're making something that is an instance of any ref, and they all have a method in them called synchronized. Now, if I do this, turns out this won't work. This does not do what I want. I still get the wrong answers. Why am I getting the wrong answers still? Well, it's because, now you might notice, hey, these counts are a lot higher. In some ways I am slowing things down. I'm making it so there are fewer collisions. This synchronized is being called on the closest encapsulating object, which happens to be the runnable. Well, every thread has its own runnable, so I wind up having 10 separate locks here, and I'm not really protecting the critical piece of code. I need to lock on something that there is one of in this instance. And it turns out that the multi-threading object is a great instance of something that I can lock on. And so what this does is, when the first thread comes in and it wants to do this count plus equals 1, it sets a lock or a monitor on this object multi-threading. The next thread that comes through has to check the monitor and say, is it free? And if it's not free, it blocks. Remember we said, well, we're going to be using that term a bit. So synchronization can cause blocking, and it's not until the other thread releases the monitor. So once it is done and it gets down to here, then another thread will be able to take up the monitor and go with it. And so if I run this, okay, that went faster than what I wanted. Let's go ahead and let's add, is 2 zeros sufficient? I want you to see the fact that this can matter, and I'd like for it so that there's a happy medium here where this doesn't take absolutely forever. Okay, so that was a reasonable amount of time. But to illustrate this for you, what if I take the synchronization out and I do that? Okay, that was much, much faster, and it turns out that the synchronized version of this code, so I want to time how long it takes for all of this to be done. So I'm going to go ahead and create a start, and I'm going to set it equal to system.nanotime, which gets the time, and then I'm going to print line down here system.nanotime minus start divided by 1e9. So I'll print out how many seconds it took for the joins to finish. And just because it's interesting to compare, what if I do something down here so that after that's all printed, I'm going to set count equal to 0, and then I'm going to increment it just in a single thread, and val start2 equals system.nanotime. We'll subtract off start2 here, redo the formatting so that this is properly indented. So basically the code that I have above is still doing the same thing. It's just I'm printing out how long it took in seconds for it to happen. And then I come down here, and instead of multi-threading, I'm just like, hey, I'm just going to add all of this up and go. And I'm also going to print out the amount of time here. And when I break it across 10 threads and I synchronize on it, it takes a little while. It takes 7 seconds to get this value. I didn't even bother printing out count down here because I know it works, whereas it only took 1.6 seconds to do it in a single thread. And now timing results turns out change. So remember those numbers, 7 and 1.6. If we run these again, we're not going to get back exactly the same answers. There are some error bars on there. 7.6 and 1.6 again. Okay, so at least these are reasonably stable. They're not varying wildly. But clearly, doing this synchronization is a bit of a problem in that you can actually multi-thread your code and make it run slower. So while synchronization prevents you from having race conditions, it can actually slow down your code. And it gets worse than that. There's another problem with synchronization. So if we get rid of this, if I have, just to kind of illustrate the problem, I'll type in something here and I'll go ahead and put it in some comments. Okay, so if I have some place in the code where I have one thread and it does a dot synchronized, and then it does some stuff, and part of this stuff is it takes and calls synchronized on some object B, and inside of here it's supposed to do some more stuff, and I can close this off. Who knows, maybe there is some more dot dot dots. One thread is doing this, so this is the activity of thread 1. However, while that is happening, I have a second thread. Now, if the second thread were synchronized in the same way, everything would be fine, because as soon as thread 1 gets into this, thread 2 couldn't start doing anything. But what if I reverse the order over here? Well, now it's possible for you to get a situation that's called deadlock. Oops. Okay. And what happens in deadlock is that you have two threads and they're each waiting on each other. or two or more threads. You have multiple threads, and they're all waiting on one another, and so they just sit there and wait forever. Now, of course, humans wouldn't do this because humans are smart, but computers aren't. And so the computer is going to do exactly what you tell it to do, and if you tell it to wait on itself, it will. So imagine that thread 1 is executing, and it gets into here, and it's doing this ... and while it's doing this ... thread 2 comes into here. And so now thread 1 has locked the monitor on A, and thread 2 has locked the monitor on B, and then this thread gets to here and it says, oh, I need B, I'm going to wait until this other thread is done. Meanwhile, this one gets to here and says, oh, I need A, I'm going to wait until the other thread is done. And so now you have this situation where both of these are waiting on the other one, and this gives you what we refer to as deadlock. Okay. There are other ways of getting deadlock as well, but it basically occurs when you have threads that are waiting for the others, and no one can complete because they're all waiting for the others to finish. So you really have to be careful and judicious about where you put in synchronized. If you put in too much synchronization, you wind up running slower than you did, and since one of our major objectives with multi-threading was to actually be able to run faster, that's really not beneficial to us. And the other problem is that if you over-synchronize, then you can have the situation where you cause deadlock. So you have to be careful with this. You should use synchronize to block critical sections of code, but even better would be to try to figure out ways to minimize or eliminate the critical sections of code. And so we'll come back in the next video and we'll look at how we might be able to do